flow algorithm. Okay, so this is just like a glossary of the terms that we're going to be using. Most of these guys are totally descriptors. Okay, so don't get overwhelmed by the fact that we've got a lot of terminology in this section. So a unit flow path from vertex A to vertex Z is simply a flow that has a value of 1. That's it. Unit refers to 1 in math. It refers to more than that, but in terms of integers, it refers to 1. So this guy, and we're going to go ahead and call, in terms of symbols, FU, U for unit. This is defined as, if you plug in E, you're going to get back 1. If E is along the path from A to Z, and the flow is going to be 0 if E is not along that path. Okay. Now, the next thing that we're going to need to look at is what are called saturated and unsaturated edges. If you think of this in terms of liquid, sometimes it helps, but you don't have to. A saturated edge is simply an edge, E, where the flow along that edge is at capacity. In other words, if you think in terms of like a sponge that got wet, that sponge, if it's holding as much water as humanly possible, and the more water you add to it will just drip out the other side, that would be it's holding as much as possible. In terms of pipes, it's at full capacity. It's totally full of your water that's flowing through. So however you want to think about it. If you're thinking in terms of shipping and trucking, your truck's full. Okay. Now, any guesses what an unsaturated edge is? Yeah, you still got extra stuff that you could push through that edge. It can be where the flow is 0 along the edge, and that does happen a lot. But the main thing is you're just not at full capacity yet. Now, when you talk about unsaturated edges, you talk about their slack. Slack is specifically how much extra you could push through an edge. So, only applies to, apparently I cannot write today, to an unsaturated edge. And this is the slack of some edge E is the total capacity of the edge minus the flow. If the slack is 0, it means you have a saturated edge. Okay. Now, a chain is simply a path in a digraph where you ignore the direction of the arrows. So a path where we ignore the direction of the edges. Now, why do we need to make that distinction? Because if you talk about a path in a digraph or in a directed graph, a path in a digraph is, by default, also called a directed path, which means when you travel from vertex A to vertex G, or vertex A to Z, or B to H, or whatever vertices you go between, as you go through the graph, you have to follow the direction of the edge. And what we're about to do with our algorithm, we're going to say we're not going to bother with the direction of the edge. Now, we're going to have to track it if we go the opposite direction on the edge of what we're supposed to, but in terms of what we're going to be doing is we're actually going to be building chains across our networks. Okay. So the path where you can go backwards on an edge if you want to. Okay. We normally say don't drive the wrong way on a one-way street, but we're going to be doing that sometimes here with our chains. And the last preliminary definition that we need before we actually get into our augmenting flow algorithm is something called a unit flow chain. This is a flow from A to Z that travels along our path from A to Z where we ignore the direction of the edges. Here, the flow along those specific edges on the chain is going to equal 1 if you're on a forward edge. So E is a forward edge, and forward just means you're traveling along the edge in the same direction that you were supposed to. In other words, you travel along the edge in the direction of the directed edge. Now, any guesses when you use the -1? Any guesses when the -1 would happen? +1 was when we traveled along an edge in the same direction as the directed edge. Yep. So the -1 would be when you go along an edge when you go the opposite direction of what you're supposed to. And we are totally going to call it a backwards edge. So we're going in the opposite direction of what we're supposed to on our directed edge. Now, if you look at any edge that is not in the chain, so edges that we didn't care about, not on the path we cared about, those guys are 0 in a unit chain flow. So now we are ready to set up for our augmenting flow algorithm. The augmenting flow algorithm is a beast of an algorithm to actually write down, but in terms of doing the work, once you've done it a couple times, it is a lot of details, but it's actually not as much work as what writing out the algorithm in a descriptive form or in words makes it feel like. Okay, I give you that warning because it is going to feel like a beast. Okay, so what you're given is you're given a network and you have some initial flow. If you are not given an initial flow, your initial flow is 0 along all edges. Okay, now in terms of notations and symbols, there are a couple of symbols that we have to worry about. The first symbol in this algorithm is P. P represents the current vertex that you're scanning from, or as your author calls it, the previous vertex. This is just like in Dijkstra's algorithm, the vertex that currently has a permanent label. It's the one we've already dealt with. So if you prefer, this is somebody with a permanent label. Okay. Now Q, this is the vertex that we've just scanned to. So this is the vertex that we've just jumped to. Your author calls it the current vertex, and that's actually a perfectly fine way of dealing it. This is the one that we are currently creating the label on that vertex. So in terms of referencing back to something we've already done, if we reference back to Dijkstra's algorithm, P would be like when we go through Dijkstra's algorithm and find the guy with the smallest length path to that point in the graph, and Q would be all of the guys adjacent to him. It turns out that is very analogous to what we're about to do. Then we have this special symbol, and this special symbol right here is the amount of additional flow that we can send through our network at this point. Okay, so this is amount of additional flow that can be sent through chain A to Q. So we don't know that that's how much additional flow that we can push through the entire network, but at this point in our stage of working, this is the amount of additional flow that we can push through at this point in time. Note, this is what you would at first glance think is the slack in that edge, but is in actuality, you have to worry about the slack across the entire chain. So you'd be watching out for how much you can push through all of the edges in the currently built chain. And again, we're going to see how that works in just a second. The formula that we're going to have in just a second here is going to give you a formula that will always calculate this value. Okay, so we will have a specific formula. And it actually looks very similar to the formula we use for Dijkstra's algorithm too. Okay. Now the actual label that we're going to put on each of these vertices when we create their label, it has two components. And the two components go as follows. The second component here is the amount of additional flow that we can push through the network up at least to that vertex. Okay? But the first one is telling you where you came from. So the P part tells you the previous vertex you were on. The plus or the minus tells you whether you followed a backwards or a forwards edge to get there. Okay? So if you started at P previously and you followed a forward edge to get to the current vertex Q, that's a plus. And if you were coming from vertex P previously and to get to Q you followed an edge but in the backwards direction, so in terms of how you progressed, in the same direction of the edge or in the opposite direction of the edge, if you follow the backwards edge, there's where the little negative is. Please note those pluses and minuses totally are coming from this notation right here of your flow along a forward or a backwards edge of the plus or a minus at that point in time. Okay. Now, the rest of this, I don't have fill in the blanks. I'm just going to go through the actual steps. I'm going to go through this relatively quickly with the actual steps because almost everybody who reads it, it has a tendency to not make sense until you actually start doing it. Okay? So the very first thing you do is you initialize your source, your vertex A, with your label. The first part of the label says we didn't come from anywhere else, so I just put a slash through it. And the second part of the label is the additional flow that you could send through the network. Because there's nothing coming previously from the source, we're going to assume we could push as much flow as we want to because we haven't gone through any edges yet. Step 2 is you start scanning from a vertex that already has a label. So if the only guy with a label is the source, you'd start scanning from A. Okay, and it already has the amount of additional flow that you could push through it, which is the second position there. So you initialize at vertex A or whatever your current vertex is. And at each one of these vertices that you're now looking at, you're going to scan your incoming edges and your outgoing edges, and they're going to be treated differently. So incoming edges, right here, you're going to look at all the edges coming into the vertex P, select all of the vertices going from it, and as long as the flow is greater than 0, we're going to go and check those other vertices that do not currently have labels. You'll change the unlabeled vertex. First part of the new label says we traveled on this edge backwards, and the second part will be additional flow. This additional flow will be the minimum of the previous flow that we were dealing with in our chain, and then the flow along the edge we just traveled. Okay. It does not matter. So the question that came in asked if it matters whether you check incoming or outgoing edges first or second. It doesn't. It just matters that you check them both. So they're independent. You don't have an edge that's both incoming and outgoing, so it doesn't matter the order. I did it here, incoming. If my handout has outgoing first, yep, sorry about that. When I was writing it up, I was thinking incoming first, and I should check with the handout to match it for you guys. Now, the outgoing edges, these are the ones that you normally think of where you're actually doing. So outgoing, well, it depends on your graph whether you have more of which type. You typically think in your head more along the outgoing way. So maybe that's why it got reversed when I was typing it previously, probably. So these are the edges where you follow your directed edges in the correct order of the direction, if you will. So you look for if there's slack along any of those outgoing edges. In other words, you could bump up their capacities, and that you're going to a vertex that's unlabeled. The new label on the unlabeled vertex will say you progressed from vertex P in the forward direction, and then the new actual additional flow would be the minimum of the previous flow we could push through the system, and then the additional flow that you're allowed through that one edge. So this minimum here, right here, is always about, are there any bottlenecks? Are there any edges that aren't allowing you to push as much flow as possible through your system? And because it's labeled flow, I always picture water and pipes in my head with these type of questions, although it's whatever you're actually pushing through the network. So step two is the main step that we're going to repeat, which feels like forever when you progress through your network. Okay, so step 2, this is the big one. Step 1 is just an initialization step. Now, when we jump down here to step 3 says check to see if so that's after you deal with step 2 at whatever edge you're scanning from, so scanning from vertex P. After you do step 2 once, You check to see if vertex Z is labeled the sink, the place you're trying to get to. If it is, we're going to terminate and go to step 4 as the termination step. If, however, you still have unlabeled vertices in your graph, you're going to choose another labeled vertex to scan from, and we go back to step 2. So like in pseudocode, this would be, your go-to step. Step 3 here, or condition 3, is you still have unlabeled vertices in your graph, but for whatever reason, you can't actually scan from any of your labeled vertices. In other words, the algorithm gets stuck. Okay? So if the algorithm gets stuck before you can actually label vertex Z, what you do is you terminate the algorithm early, and you set P to be the set of labeled vertices. P complement would be your unlabeled vertices, and you're pulling a specific cut. The cut would be P complement, and this is a fully saturated cut, which means you've actually reached a maximum flow at this point. There's no way to tell that you've reached a maximum flow until you get a fully saturated cut. Okay, so this is how you prove that, hey, we already had a maximum flow previously. Now, if we actually do get that vertex Z gets labeled, what that means is we can push more flow through our network. And step 4 tells you what you do. In terms of the actual label on Z, the label on Z, where's the label? The second part here tells you how much additional flow you push through the network. And step 4 shows you how to build an AZ chain K. You basically track labels, and I'll show you how to do that. And those tracked labels are actually going to show you which edges in your originally given flow are going to have their flows either increase, where you're going to be able to push more labels through, or decrease if you really shouldn't have put that much flow on that edge and you need to move it to a different edge. Okay? So that is a ton of theory and procedure. This is why I would recommend having that handout next to you when you're working these problems, okay? At least for the first couple of times. So let us start working on an example, and